Swayam Prabha. Digital India. Educated India.
Now again, if we take the approximation and neglect this current, okay, so one more approximation if we take that the secondary current I2, so if we approximate this again circuit and remove this vertical limb of the circuit, so the transformer can be represented simply by this circuit. So here you have V2 prime, here you have V1, here RE1 and XE1. This is the finally approximated circuit. Okay, so the equivalent circuit of transformer with some approximation. So we can write this transformer by T by F or sometime Tx depending upon the understanding or reference. In short, with approximation. Okay, is this clear? So we did all this approximation to get a very simple circuit. So all the engineering purposes applications for the X by R ratio, if you see in future for power system engineers, the X by R ratio is a quite important parameter while studying the power transformer or the distribution transformers. So we can calculate that ratio by assuming this approximation, but now onwards we'll be having some circuits where approximation is allowed, or somewhere we say that we have to consider this magnetizing component of current. That depends upon the question. So let us draw the equivalent phasor diagram, okay, of a complete circuit. So in this case, if you want to draw the phasor diagram, so this current can be I1 or I2 prime. So taking the reference which is going here as I2 prime, okay, and we want to draw the phasor diagram. So let us draw the phasor diagram with a lagging power factor load. So one, I can give an example. Suppose your reference is V2 where the load is connected and the load is a lagging component which is I2, okay, and the angle here phi 2 represents the phase difference angle of the secondary side. Then I can write this little somewhere here, V2. So I2 R2 will be loss in phase, in the phase of current. So this is nothing but I2 R2 equivalent resistance of secondary side. So this is basically the primary side. Similarly, if we refer this on the secondary side, this will be the circuit. V2, I2, RE2, XE2, I1 prime, V1 prime. So this is the equivalent circuit. Refer to the equivalent circuit of transformer, refer to secondary side. Okay, so we are actually drawing for this, and XE2 will be the 90 degree of this component which is here I2 XE2, and this is a net I2 ZE2, and V2 plus this drop, V2 plus this drop is nothing but V1 prime. So this voltage is nothing but V1 prime, or we can this E2 by A. sorry, A times of E2, right? V1 prime is nothing but E2, which is nothing but V1 by A. This is how we can write it. So this is the approximated phasor diagram. What if you would like to draw a complete phasor diagram? So let us understand that. So after that, we'll go to the voltage regulation. So we'll do the complete phasor diagram. Okay. So what we can do, we can assume that reference as V2. It is little complicated. You have to pay little attention. So this is V2, and the lagging current is flowing, which is I2, and here you have I2RE2 component. You remember the circuit, or let us look at the complete circuit so that we will do with this. We'll go with this circuit, right? So complete circuit we'll draw. So let me have the complete circuit here, and then we cannot draw close to that, so we'll just shift it down somewhere here. So now you can see clearly here. So this is V2, and now this is your I2x E2. This component is your E2, which is this E2, correct? After that, it will go to the E1 side. E1 is equal to E2, right? Or the turns ratio will be E1 by E2. So this will be having, suppose, step down or step up, that we can figure it out based upon the A, which is the turns ratio. So suppose it is a step up transformer, E2 is greater than E1, so E1 will be some portion of E1 thing, then opposite of E1 will be V1 prime. V1 prime is assumes of voltage, which is here. Okay, now this V1 prime, now where will be the magnetic flux? Now we'll consider the magnetic flux, which will be having the 90-degree phase leading to the E2. So it will go 90 degrees of E2. So this phase angle is 90 degree, because this is the component close to the magnetic core, not this. This will be coming after the drop. Okay, this is what is here happening. E2 and V2, there is a drop of this I2ZE2. Correct. So the 90 degree here, it will be phi m, and phi m will be having a current I mu, right? And I mu plus IW. IW will be the component which will be having in the direction of V1. Okay, so we can write the component here IW. Okay, and this total current will be your I naught. So let us put some attention. Sorry. So let us assume this value a little higher so that you can just clearly see the effect of. So this is your I naught, and the opposite of I2 is I2 prime, which will be this. So this line which I am trying to draw, basically the exact 180 degree phase shift with I2. Prime. And then I2 prime plus I naught. I2 prime plus I0 is I1. So if you add these two current, if you add, this is nothing but your I1. And the current I1 which is being drawn, I1 and sorry, this component will be parallel. So this is I1 RE1. Similarly, this is I1 XE1. So this is what? I1 ZE1. And this complete component is nothing but V1, which is applied here. Okay, so V1, then drop of R1 XL1 is drop, then this is V1 prime, which is here across this, and then we have E1 which is opposite to this phase, then E2 which is A times of E1, then E1 which is having drop between R2 and XE2, and then we get V2. So this is a voltage side, and close to this is the current side. So this is how you're going to draw the complete phasor diagram of a transformer. So this is very interesting and quite important when we try to understand the circuit philosophy of this current, which is leading, which is lagging, which is the in phase component, which is out of phase component. So the current or the phase load power factor is this one. Okay, so this is phi 2. And the primary side, what is the phase, which is nothing but I1 and V. So I1 is this and V is this. So this is nothing but the phi 1. So after understanding the complete phasor diagram of exact equivalent circuit of a real or practical transformer, okay, all the non-idealities are considered, we'll try to understand the some performance parameters. So next quantity which we are going to discuss is voltage regulation. Okay, so the name suggests it is a variation. So let us define it before we go to the mathematical derivation. So the voltage regulation of a transformer is defined as the arithmetical difference of the secondary terminal voltage between no load to full load. Between no load means what? I2 is equal to 0 to full load. Full load means I2 is nothing but I2 FL, rated load, at a given power factor. Okay, means the load is fixed with the same value of primary voltage for both rated load and no load. For the same value of primary voltage for both rated and no load condition. So mathematically the voltage regulation is defined as V2 at no load condition, which is I2 0, and the difference V2 and full load condition, right? So the arithmetical means like magnitude of these two, the difference. Okay, where V2NL is secondary voltage of no load condition, secondary voltage at full load condition. So per unit regulation is defined as V2 no load minus V2 at full load divided by V2 at full load. And if you want to have a percentage, you can multiply by 100. So this is a per unit voltage regulation. The condition under which the regulation is to be figured is a rated voltage. Okay, so the condition which is making this voltage regulation is a quantifiable quantity, or it is calculated under rated voltage, current and frequency. And when we do not want to know, like if you want to have a voltage regulation at a specific load, then I mentioned that 80% load means we can consider that is 0.8 times of full load current. So we can define the values at which we want to calculate the voltage regulation. If nothing is mentioned, we will assume that full load condition. So this is the by default assumption. Otherwise, we'll be given that what is the loading, what is the load connected, and how much rated ratio, or like the rated load, which is a fraction of that, can be taken as per the question. And the power factor of the load should be mentioned. If the power factor is specified, it's fine. If it is not specified, we assume it is to be unity. So these two conditions you have to be make sure. Let us write these so that we should not forget. If power factor is mentioned, then no problem. Is not mentioned, assume it to be unity. Secondary, if the load current is not mentioned, I mean what is the loading of your output side or the secondary side, assume full load. Otherwise that load will be given 80%, 70%, 3%, 10%, whatever. Okay, now we can calculate the voltage regulation at different load, like if load is inductive, or load is purely resistive, or load is capacitive. And you can find out that the mathematical understanding is same, but in case of regulation at unity power factor, the phi 1 or phi 2, the output side power factor will be unity. So under that condition, if you want to calculate the power factor, so there will be three conditions of the load, right? The possible load condition can be inductive, capacitive, and resistive. So inductive means you have lagging phi 2, capacitive means leading phi 2, resistive means phi 2 will be 0 or will be in phase of voltage. So that phi 2 will play a role when we want to calculate the voltage regulation. And similarly, if we want to calculate the voltage regulation at unity power factor, then we have to consider phi 2 can be 0. So that depends on under what condition you want to compute the voltage regulation. Okay. So if it is for percentage, so this is per unit PU, and similar voltage regulation can be written as V2 at no load minus V2 at full load divided, sorry for the bad writing, let me rewrite it, V2 at no load minus V2 at full load divided by V2 at full load. This is per unit into 100. This becomes in percentage. Okay. So there is no unit to the voltage regulation because it's a ratio from voltage to voltage. So the unit is V by V. Okay, so now after this, let us consider one example on calculation of voltage regulation. Then we can quickly find out the solutions, right? So, or first we can understand the last important topic, which is per unit concept. and after per unit concept we'll be having some questions where we can handle these things. Okay, so let us talk about the per unit concept. So we'll define some per unit resistance, per unit quantities. So as the name suggests, we'll be having quantities with respect to some equivalent or base quantities, right? So full load drops occurring in the transformer can be expressed as a fraction of the full load terminal voltage, and we can consider that fraction as a per unit representation. So we can like nomenclature we can represent is R equivalent per unit. So this is nothing but per unit equivalent resistance. So per unit equivalent resistance. Okay. Now, if you want to calculate the per unit equivalent resistance, we can write it as R equivalent per unit is nothing but the total I full load which is flowing in the primary side, I1 full load into R equivalent of primary side as a ratio of V1. So this is will be equal to the I2 full load with the R equivalent resistance by V2. So basically we have R base, which is nothing but rated current or rated voltage by rated current. Okay, so rated voltage can be your V1 or V2, and the rated current can be I1FL or I2FL. And now RE per unit is equal to RE by RE1, which is equivalent resistance of primary side, by the base resistance of primary side, and RE2 by V2 by I2FL is base resistance. Okay, so this is the base resistance. Similarly, you can calculate the base reactance by the same logic. So XE per unit is nothing but, so we can calculate it Z base rather than calling it as a S base, we can call it as Z base. So it is nothing but X1 by Z or X2 by Z. This is one primary side and this is secondary side. So XE1 Z1B is nothing but rated voltage by rated current. So this is ZE1, this is ZE2. So this you can call it as a kind of V2 by, or primary side we'll write, so V1 by I1FL, where it can, sorry, this is not equivalent, this is AND. The magnitude will be equal, or we can write it as ZB2 similarly. Okay, and so XE1 I will go up, I1FL by V1. Similarly, we can calculate the other quantities per unit base and define the per unit quantities. So that we'll see where you can use this per unit concept. So Similarly, the voltage regulation can also be described in terms of per unit quantities. So I'll just write the formula. You can just have a look and understand clearly. So if we write down the voltage regulation, of basically in per unit quantities, okay, so voltage regulation per unit quantities we have to compute. So it will be nothing but V1 by A minus V2 base value divided by V2 base value. Now we'll be seeing what is a base value. This is nothing but voltage regulation. Okay, and into 100 if you do, it will be percentage. Okay, so this is the arithmetic values. Now if you want to do per unit, you have to divide it by base, which is taken as a secondary voltage. Okay, so if you divide V1 by A times of V2 base minus 1 by 1, which will be V1 per unit minus 1. Okay, this is nothing but V1 per unit, correct? Into 100 is percentage, and this, sorry, this is nothing but multiply by 100 percentage. This is per unit voltage regulation. So the concept of per unit is similarly applied here for the voltage. So let us just find out the per unit thing. So we will be considering any base voltage. Suppose the output voltage, which is rated V2, consider as V2 base, which is a base voltage. Okay, so V2 per unit will be nothing but V2 by base quantities, which is VB, so which will be nothing but V2 by V2B, and V2 and V2B are same, so this will get cancelled out 1. So V2 per unit is a reference voltage, which is unity. Now with respect to unit, we will be defining every voltage. So what is here we did? Here we have divided by V2 PU so that per unit reference is calculated. If you want to calculate V1 per unit, it will be nothing but V1 by V2B. And if it is referring, then this term will appear here. Okay. So if we refer this per unit quantity to the primary side, then the term A will come. So this is basically the base for the primary side, V1 PU. Okay, so V1 PU nothing but A times of V2B. So this is what we did in voltage regulation side. Okay, so with this the voltage regulation part is done, and you can always solve some examples. So now if we try to let us solve one example on the per unit concept. Okay, so let us consider one example. A transformer has 2% resistance. A transformer has 2% resistance, 5% reactance, okay, now find its voltage regulation. at full load and 0.8 power factor lagging. So this is the condition which is given. Now full load is defined, power factor is defined, the reactance and resistance is defined. Okay. Now if we look at the approximate voltage regulation, then voltage regulation in per unit can be approximated to Re per unit cos of phi 2 plus Xe2 sine of phi 2. So this you can derive. I'll give this problem in the kind of assignment where you can derive this approximate per unit regulation with given power factor. So now if you put these values, the voltage regulation will be given as 0.02 times of cos of phi 2 is 0.8. Okay, so 0.8 plus 0.05, which is Xe1 per unit or Xe per unit, into 0.6 sine phi 2, and if you solve it will come around 4.6%. So this will come in per unit, you can multiply by 100, then it will be percentage. So now with this, one of the next parameter which is important to define any electrical element is the efficiency. So if we consider some of the losses, right, so we have earlier seen the separation of hysteresis losses. So the total losses which happen in the transformer, which is little, have some significance, otherwise there are so many losses like dielectric losses, heating in the oil, and then we have stray losses. So ignoring them, the two major losses in the transformer. So if you talk about the losses in the transformer, we have two types, right? First is iron loss, Pi corresponding to iron loss, and Pc, which is corresponding to copper loss. So these two losses are the kind of significant component of any loss, where Pi having a two component, as we have already discussed, P and Ph, okay, that are proportional to frequency and the frequency square, and then the copper loss is basically the I square R loss. Okay, so this is corresponding to the copper loss, means the conduction. So the total copper loss, if we define, it will be nothing but I1 square R1 plus I2 square R2, right? These are the losses which is having primary side or secondary side. The total loss is given as a copper loss. The important thing is, if you recall, I1 by I2 is nothing but N2 by N1. So from here, copper loss can be given as, like if you substitute these values and take the common I2 square common, so you will get R2 plus N2 minus N1 whole square by R1, so which is nothing but I2 square RE2. Okay, this is the secondary current, and this is the total resistance, equivalent resistance referred to the secondary side, right? Because that is the side where the load is connected. So we are referring to the, so this is total loss when equivalent resistance is referred to secondary side, correct? This is secondary side. This is one of the important thing, and it is, if we consider the complete resistance on the primary side, the total loss will be same, which is I1 square RE1. Okay, and it will be same as I2 square RE2. Sorry, I2 square RE2. This quantity will not change. Okay, then we third loss, which is I talked about, stray loss. So stray loss basically the losses which is happening due to the leakage flux, or kind of the losses which is being produced by the indirect effect of eddy currents, because that is also will be producing. And then we have dielectric loss. Okay, but these losses are normally negligible. Compared to the rating of the transformer, these losses are negligible. So we'll be most of the time considering these only two losses, the iron loss and the copper loss, for calculation of efficiency. So now how do you calculate the efficiency of a transformer? The efficiency is nothing but the output power upon input power. Okay. So efficiency represented by eta is mathematically defined as output power by input power, right? Ratio of output to input. So output power by input power. So what is output power? If you mathematically look at the output power, which is nothing but V2 I2 cos phi 2, and input power is V1 I1 cos phi 1. Am I doing some mistake here? Or just to keep the component on the secondary side, we can just rewrite it as the output power divided by output power plus losses. Losses means 2, iron loss plus, or we can write Pi plus Pc. Losses means Pi plus Pc. So here in this case we can write it as V2 I2 cos phi 2 plus the iron loss will be nothing but Pi plus I1 square times of R1 plus I2 square times of R2, and then if you want to remove this, you can have this R2 prime. So we can write it as P C is the copper loss. Okay, and in the percentage, if you define, this is per unit, and if you multiply the same quantity by 100, it will be percentage efficiency. So since the transformers are in the service all day, so we do not consider the momentarily what is the efficiency of the transformer. What we are interested in considering is the all day efficiency. Okay, so if we consider the all day efficiency, we consider energy. Okay, so efficiency at all day is nothing but defined as energy output over 24 hours by energy input over 24 hours. For energy input is same as like energy output plus losses, so that you can do, and we'll see how we use this for calculation of all day efficiency. Okay, so when we talk about the efficiency in terms of like the component, then we have to understand that at what condition the efficiency of the transformer will be maximum. Okay, so what is the condition for maximum efficiency?